All right, I guess we can start now. Good evening, everyone, and welcome to day two of the IIT SP Bootcamp. I hope you enjoyed our last session and got a good introduction to the world of autonomous drones and flight control systems. Today, we're going to build on that foundation by exploring some of the most important technologies that make our drones possible. Today, we'll be learning about Pixhawk flight controllers, the ArduPilot ecosystem, and QGroundControl, which together form one of the most widely used open source drone platforms in the world. We'll also take a step back and understand the physics behind IMUs, how accelerometers and gyroscope measure the motion, and how sensor fusion combines that data from multiple sensors to help a drone accurately determine its position and orientation. By the end of this session, you'll have a much clearer picture of what happens inside a flight controller and how software and hardware work together to keep an autonomous vehicle flying reliably and safely. So let's get started. And one small rule, we will have to keep you on mute during the session, but if you do have any doubts, please feel free to put them in the chat section and we can clear them. So let's begin. Am I visible, audible, and can you all see my screen? Hello, can you all hear me?
Yes, yes.
All right. Can you all see my screen?
Yeah, it is visible.
All right. So let's begin. This is part two of the ITSP bootcamp. So these are the topics that will be covered by me. IMU physics will be taken by Jeevan and sensor fusion would be covered by Divyansh Goyal. So let's begin. Introduction to Pixhawk, ArduPilot and QGC. So before I officially begin this lecture, can any one of you all tell me what is an autonomous drone or an autonomous system in short? In short, I'll wait for 10-15 seconds and you can put your answers in the chat box. I'm still waiting, guys. You can put your answers in the chat box. I'll repeat the question. What is an autonomous drone? And let me know if you have flown or at least seen a drone in real life. You can maybe raise your hands or give a quick reaction. All right, I see an answer by Sejal that can make some decision itself. That is correct. That is an autonomous system, perfectly defined. All right, so let's move ahead. So, what is an autonomous drone? We can maybe think of an analogy of a Google Maps. So, if you have used Google Maps, you know that you enter a destination, the app auto calculates the best routes, and the most important part, it keeps correcting itself while moving. And this analogy can also be applied to autonomous drones. So, how it does this is based on Pixhawk, ArduPilot, and QGC. So, the brain of the drone is the Pixhawk, the software of the drone is the ArduPilot, and what controls these things is the app Q Ground Control or QGC for short. Moving ahead, this is the general the architecture that we'll be developing throughout this session. So here we see that we have the Pixhawk flight controllers, and we also have some other controllers and sensors. These can be connected via SPI, I2C, or serial ports. And here we have the operating systems that are the Linux one that we might have heard of, Visible Linux, and some other variants as well. Then we have the flight code that goes onto the drone. So the computer drone is the Pixhawk, and the program or the code that goes onto the Pixhawk is the ArduPilot code, and that contains vehicle-specific flight code. For example, it would be different for a plane and for a drone, for a fixed wing and for a free wing. It also has some shared libraries for sensors and EKF. EKF is short for extended carbon filters that will be covered by the Vyansh Goyal in sensor fusions. And it also has an hardware abstraction layer. Now we have the communications layer that is the Mabling protocol. So this is the connection between the flight code and the ground code of the ground station. And this ground station can run on a companion computer. For example, we have the Raspberry Pi. Moving ahead, what actually is Pixhawk? So this is the image for a Pixhawk controller. And basically, it is a small computer called a flight controller, which is used to control a vehicle, drone, RC planes, boats, or maybe some other things that you want to control autonomously as well. Without Pixhawk, a drone can only follow pilot joysticks commands. But with Pixhawk, the drone can stabilize itself. It can hold its altitude in the Z direction. It can autonomously fly to GPS location set by us. It can also return to home automatically, which is a very important feature. And it can also follow missions by itself for complete autonomy. It consists of built-in sensors like the accelerometer, gyroscope, magnetometer, barometer, etc. And most importantly, it is open source, which means it is free to use, highly customizable, and easier to use. This is the general architecture of a Pixhawk controller. As we can see here, we have the GPS connection or the GPS module. We have the ground control station over here. We have the debug port. We have the cameras. We have the receivers for it. We have the telemetry radio over here. We also have servo motors. This is the power distribution board and the ESCs that we have covered in the last section of the bootcamp. And we also have the LiDAR sensors, some remote IDs, and we also have the DSM RC and the drone can GPS modules over here. Moving ahead to the sensors in Pixhawk. So Pixhawk is a flight controller that has various sensors like the accelerometer, gyroscope, magnetometer, barometer, as said. And I'll just quickly cover these. Accelerometer is a small sensor that measures linear acceleration in all the three directions, that is X, Y, and Z direction. And how it does this is using MEMS technology. MEMS stands short for micro electromechanical systems. So what happens is we have some sort of comb structure interlocked like this. And with linear accelerations, this can move relative to this. And the distance between these plates changes, which causes a change in the capacitance. And this capacitance can be measured electronically and converted to signals. And it is repeated thousands of times to give the exact data for us. A gyroscope also works similar to this, but a gyroscope is used for angular measurements. That is the pitch, roll, and yaw axis. It is also prone to errors like the gyro drift that we'll see later. A magnetometer, as the name suggests, it detects the Earth's magnetic field to determine the orientation of the drone. That is, if the drone is heading in the north, south, east, or west directions. And the barometer, as we all might know, is something that uses atmospheric pressure to estimate the altitude. And a small note for future, sensor fusion in flight controllers is the process of combining data from multiple onboard sensors to sort of process that data altogether and spit out some values for the position and heading of the drone. That will be covered later during the course in sensor fusion topic. Moving on to the external GPS module that can be attached. GPS, as we may know, stands for Global Positioning System. It is one of the global satellite systems that provides geolocation and time information to anyone who just has a GPS receiver. Now, the working of GPS, it works using the satellites orbiting the Earth. A GPS or a GPS receiver in a drone or a phone listens to these signals and calculates how long each signal took to arrive at that position. Using this time difference from different satellites, it computes its exact position through trial iteration process. With at least four satellites, the GPS can determine the latitude, longitude, altitude, that is the height, and almost accurate time almost anywhere on the Earth. And if the user is moving, they can also determine the speed and direction of the user. Addition of the GPS module to the Pixhawk enables us to use features like autonomous flight, return to launch, which is a very important fail-safe, as we'll see later, surveying various areas, delivery services, and also for military surveillance, etc. Now, moving to other modules. So we just saw the GPS module. And moving on to these other modules, we have the LiDAR next, which just sends out lasers light, and it tracks the time it takes for the light to come back to the drone itself. And using that time difference, it can calculate how far the obstacle is. It is generally used in low altitude flight stability, mapping, and also SLAM. SLAM stands short for simultaneous localization and mapping, which we'll see later, and object detection in autonomous navigations, etc. We then have the optical flow sensor, which measures motion relative to the ground to aid position hold and stabilization, especially in environments where GPS does not work. So it is useful for indoor flights and also for precise hover in confined areas, position hold, that is to hold its position in the X, Y, and Z directions. Then we have the thermal sensors, which can detect heat signatures useful for search and rescue, wildlife monitoring, and also industrial applications, like for chemical engineering plants. General use case includes nighttime or low visibility navigation, hotspot detections in firefighting, thermal mapping in agriculture, etc. The next module is the INS, which uses motion sensors to calculate the drone's position, velocity, and orientation by measuring the acceleration and rotations over time. We now have the pitot tube. It is a tube that uses Pascal's law. Sorry, I apologize for that. Not Pascal's law, but the P plus rho g h plus half rho v square. That is the Bernoulli's equation to calculate airspeed of the drone or the fixed wing flying through the air. It is an airspeed sensor that measures the dynamic pressure of airflow to determine the true airspeed of a drone. It is commonly used in fixed wing and VTOL drones for stall prevention, accurate navigation, and efficient flight control. And last but not the least, we also have a tachometer. It is used to measure the rotational speed of the motors or propellers, which is crucial for monitoring the motor performance, detecting faults, and also improving control algorithms, as we'll see later. Moving ahead, we now have drone stabilization. So, can anybody tell me what a PID controller is? We have studied this in our MS 101 lectures, so let's see how many of you are studying. Uh, can anyone please put in the chat box if you all remember? That is right, that is proportional, integral, and derivative. And can you tell me what a PID controller does? It corrects the error as said by AM. Not exactly. It is something used to control the future states of a system that we would like to control. I'll go over it more briefly. So a PID controller is a system that helps a drone or any system that you would like to reach stable to stay stable and reach the desired position smoothly. And in drone using Pixhawk, PID constantly checks what are its current angles in the pitch, roll, and yaw directions, and its speed in the XYZ directions, and how far is it from the required state. It then adjusts the four motor speeds accordingly. KI integral ET dt plus KT time derivative of ET, where UT denotes the output signal, ET denotes the error term, while KP, KI, and KD denote the gains for the system. That is the proportional, integral, and derivative gains. I also have attached a reference video if you all want to see further. And to learn about this more, I have a small example for you all. So this is what a typical control looks like. So the problem statement for this is, suppose we want a drone to hover at some position XYZ. So how can we achieve that? So using 6 PID controllers, the pitch, roll, yaw, and thrust. Sorry about that. Using the pitch, roll, yaw, and thrust inputs, we can put them into the motor mixing algorithm, that is MMA, that gives drone inputs or controller motor inputs to the mini drone, which are then sensed again and fed back into the PID system to form a closed loop feedback control system. And how it does this is using a reference signal. That is, we have the reference position, for example, at 00. So we want the drone to hover at 00Z. And so it inputs this to a world to body conversion. That is from the global world to the reference system of the drone. And then it uses the pitch and roll PID controllers to sort of get it over 00. So for example, if the drone is hovering over 3, 4, then it would use the pitch and roll commands to get it over to 00. And then using the pitch, roll, yaw, and thrust, it would keep it at the same position using an altitude reference for the thrust. Moving ahead, we have the connections. So it also, the Pixhawk flight controller uses two main types of connections. That is the UART and the I2C. So it also uses SPI. It is not a semester performance index. It is the serial port inputs. So using the two main lines in the UART, that is the TX and RX. One small thing to note is we have to connect the TX of one device to the RX of the other device and vice versa. Now, devices that can be used for UART connections are GPS modules, telemetry radios, receivers, the Raspberry companion controllers, etc. And it is different from I2C because I2C is a synchronous serial communication protocol that it uses several inputs at one time. It only uses two wires, that is the serial data line and the serial clock line. It has a master to slave architecture, and typical I2C devices on the Pixhawk include magnetometers, barometers, IMUs, digital compasses, etc. And I'm sorry about this. SPI is not your serial performance index, but it is the serial peripheral interface. It also uses PWM, pulse width modulation, as we have seen in MS101. It also has ADC, that is the analog to digital control converters, and it also has USB and SD card inputs. Moving ahead, we have the safety features for our drones. One very big tip for this hobby is if you want anything to move autonomously, we should have some fail safes in place so that if anything goes wrong, we do not damage any people, property, or animals, or anything in general. So we need to keep our safety features in check. So some of them are listed over here. We'll go through them one by one. So the first one is arming check. That is performed before the drone starts its motors, and it verifies the sensors, GPS, battery, and system health to ensure that the drone is safe to fly. And what is a failsafe? It is a protective feature that automatically takes action if something goes wrong, such as a case of signal loss, low battery, sensor failure, connection loss, etc. Moving on to GPS failsafe. It activates when the drone loses GPS signal or position accuracy. The drone may also switch flight modes or land for safety. We also have the battery failsafe, which is very important for electronic systems. It is triggered when the battery voltage becomes critically low so that the drone does not crash out of the sky. It can then automatically return to home or land to avoid crashing. We also can set up a geofence, that is a virtual boundary set using GPS that prevents the drone from flying beyond a specified area or altitude. And these are some of the variants of the flight controller PX4. So we have the Pixhawk 4, we have the Cube Orange Plus, and we have the Pixhawk 6X. And just a small note, companion computers include microcontrollers like the Raspberry Pi. Moving on to ArduPilot. It is an open source autopilot software used to control drones, planes, helicopters, boats, rovers, and other autonomous vehicles. So these are the different softwares that are available to us. And we will be using ArduPilot for our drones. It also runs on flight controllers like Pixhawk and tells the vehicle how to stabilize itself, how to fly autonomously, how to follow GPS waypoints, and how to respond to emergencies. That is using the fail safes. It is very popular because it is free and open source. It is very customizable. It is very reliable. It is used in industry as well, and it has a huge community support to it. Moving on to flight modes in the ArduPilot system. So it has a lot of built-in modes for flying. Some of them include stabilize, alt hold, loiter, auto, and RTL, that is return to launch. So taking a look at them one by one. The stabilize mode is something that holds the drone control, but a pilot can also take over manually anytime he wants, and it keeps the drones fixed in the X, Y, and Z positions. We also have the alt hold that keeps the drone fixed in the Z direction, and it happens by using sensors like the barometer. The pilot can also take over anytime they want and control directions and move. Next, we have the loiter mode that is used to hold its position and altitude. That is the X, Y, and Z mode. And even if you release the controls, it stays hovering in the same place. That is different from stabilized mode. And the next is auto mode. So it is basically like we fed in a program to the ArduPilot software, and it can follow that pre-programmed mission with GPS waypoints to include taking off, landing, navigation, also maybe using systems like a gripper to pick things up or load things down. And the most important feature of the flight modes is the RTL or return to launch. In this system, the drone flies automatically back to its takeoff location and lands. It is usually triggered during fail-safe conditions like low batteries or signal loss. Moving ahead, we also have autonomous navigation, and it means that a drone can fly itself using GPS, sensors, and pre-programmed instructions instead of control from the pilots. In ArduPilot, the user creates a mission using softwares like QGC, mission planners, etc. The mission usually contains information about the GPS waypoints that we can see over here, the altitude values at what heights do we want the drone to fly, the speed settings, how far do we want the mission to be over, and also actions like taking photos or using grippers or landing. And just a small note, ArduPilot uses techniques like sensor fusion and EKF for determining an accurate estimation of the drone's position and velocity in the autonomous mode. And if you all want to learn more about this, you can also join our aerial robotics course that will be happening in Learner Space in the coming week. Moving on to Mavlink. If you all remember from the architecture, this is the communication that happens between the drone software and the ground software. So the companion computer and flight controller communicate via serial connections, that is the UART, using the Mavlink protocol. And the short form for Mavlink, or the long form for Mavlink, in fact, is Micro Air Vehicle Link. And it is a lightweight messaging protocol for communicating between the drones and ground stations, or even the onboard computers. It enables the exchange of commands, telemetry, that is the data that we record using our drones, and also sensor data. And we can use the TLM2 or the TLM1 port on Pixhawk to connect to a companion computer. And we have this reference for you all to check out if any more information is needed. Moving on to QGC. QGC or QGround Control is an open source software that allows you to fly and plan missions for any Mavlink enabled drone. With QGC, we can see live battery level, GPS, altitude, etc. It can also allow us to calibrate sensors and configure settings. And it also acts as a remote control and dashboard for our drone. Using QGC, we can plan autonomous missions, set GPS waypoints like we see here, and we can also monitor live telemetry, that is the live data that we record on the drone. We can also change flight modes, for example, from stabilize to hover to loiter. We can also calibrate the sensors in our drone. We can also tune the PID settings, that is the KP, KI, and KD gains. We also can view the maps and fly paths, and we can also update the firmware on our drones. Moving on to calibrations. Sensor calibration is the process of teaching the drone sensors what the correct reading looks like so that the drone does not fly itself into the ground. It also allows the system to fly by wire. This is just a phrase that if anyone says, we know that it can allow itself. It can allow the drone to fly itself basically.
And some examples of calibrations include the accelerometer, the compass, radio calibrations, and the level horizons. So the accelerometer just teaches the drone what level orientation is. The compass sets the accurate heading direction, that is, it calibrates the north direction. The radio calibration that maps the transmitter stick movements from our transmitter to the pitch, roll, yaw, and thrust directions. And the level horizon check also ensures stable hovering. Moving on to telemetry data. Telemetry monitoring is the basic process of viewing the live data from our drone while it is flying. And QGC receives this information from Pixhawk using the Mavlink communication protocol. Some important waypoints that we can use are its position, its height, its speed, the battery voltage, which is very important, the flight mode, also very important, the signal strength, pitch, roll, yaw, and distance from home and mission progress. Moving ahead, we have the log analysis and debugging. So log analysis is the process of reviewing the recorded flight data, that is reviewing our telemetry data to understand how the drone performed during a specific mission. Pixhawk stores this log data and it contains data from the GPS, the sensors, the battery status, the flight modes, errors, etc. In QGC, these logs can be analyzed to detect problems and improve performance. It can help us identify issues such as drone drifting, GPS loss, vibration problems, sensor errors, and also poor PID tuning. And just a small note, poor PID tuning leads to us able to control the drone very sluggishly. That is, it does not follow the commands as specified by us. Now we'll move towards the end of my session. So the entire workflow that can help you to design a drone from scratch. So this is the first step. That is, we build the hardware of the drone, the body of the drone that is. Then we connect the Pixhawk to the computer using USB cable or telemetry. Then we install the firmware, that is the program inside QGC. We flash the appropriate ArduPilot firmware. We then calibrate the sensors using QGC. And then we use the ArduPilot software to configure the airframe. That is, we give ArduPilot the information about the motor layout on the drone and the electronics, that is the ESC, motors, etc. We then calibrate the GPS and compass. Then we configure the fail-safes. That is a very important step. That is, we configure the battery, GPS, radio, and RTL fail-safes at least. And then we perform the arming checks for the drone. And then for the first takeoff, we tend to fly it in stabilized mode. That is, we perform a short flight to confirm the proper response for our given inputs. And then we create an autonomous mission in QGC and upload it to the Pixar computer. We then arm the drone and switch it to auto mode to allow it to fly autonomously. We then monitor the telemetry from our ground station in QGC. And then at the end of the mission, it can return to launch or it can auto land depending on what the protocol that you have set up. Then at the end, when it has landed and de-armed itself, then we can download the flight logs, check and debug for any further updates. Uh, Moving on, uh, we have SITL, that is software in the loop. It is a virtual drone simulation where ArduPilot runs on your computer and flies a virtual drone instead of crashing your real drone in case anything goes wrong. And we can use it to test parameters like our mission planning, our waypoint navigation, our RTL mode, our PID tuning, our takeoff and landing, our telemetry monitoring, and also most importantly, the fail safes. So moving on to some common mistakes that beginners can make. Please pay attention to this slide as this is very important and something that you should keep in mind when designing your drones. So the first big mistake is ignoring the center of gravity, which leads to it being pendulum unstable, and the poor weight balance makes the stabilization difficult. Flying with a low battery voltage, this is just something that I'll point out. When flying a drone, it has a maximum flight time of around 5 to 10 minutes. And so beginners often make the mistake of underestimating how quickly this voltage can drop, especially when we have motors, sensors, cameras running all around. The next is improper frame vibration isolation. So this can lead to noise in our sensors, which can then confuse the EQF. Then we have the incorrect propeller orientation. That is, if we, for example, install a clockwise rotating propeller on an anti-clockwise rotating motor. So that would not give us any sort of lift. It would in fact take our drone down. So the wrong prop direction is one of the most common reasons drones flip during our takeoff. The next is a battery selection. So it is highly recommended to use an overpowered battery, but keep the throttle at around 50% so that using an underpowered battery can does not cause a voltage drop or unstable flight. So we basically do not want to run out of our fuel, that is the battery voltage, when we are flying the drone. The next is not checking compass interference. That is the magnetic interference can cause incorrect heading estimation, which is something we do not want because we do not want our drone to fly off in one direction when we meant the other direction. The next and the most important one is not securing the flight controllers, the battery properly. Losing the mounting can loose mounting can cause inaccurate IMU readings that can lead to confusion in the EKF. And a good way to properly mount your batteries and flight controllers would be using a Velcro system. And these are some of the future projects that can be done using this technology. So we first of all have the SLAM, that is simultaneous localization and mapping. So what it does is, imagine we have 100 square meter level field of open area basically, and we can then fly our drone without GPS, and it can take photos continuously. It can process how those images translate from one image to the other. So that is called localization and mapping. So it does them simultaneously. Hence, it can map out where it is going, and it can also make predictions and continue its autonomous flying without using SLAM and without using GPS. So SLAM is basically a shorthand, I would say, option for using GPS. The next is AI navigation. The best one personally is swarm drones. The next one is computer vision that can be used to, for example, identify crops that have grown and are still growing in fields. Then we also have auto obstacle avoidance in autonomous systems. We also have autonomous target tracking that can be used for defense purposes. We also have drone to drone communication. We also have precision landing systems, and these can be used for search and rescue missions. Then we have the BVLOS, sorry. We have the BVLOS operations, that is the beyond visual line of sight. So in this project, we can have two drones talking to each other when they cannot see each other because of the curvature of the earth and the horizon bending away from us. So this is some of the technical jargon, or I would like to say the summary. If you did not understand any of these words, then we have a list for you. So the flight controller is the main onboard control computer. The firmware is just the software inside that controller. The telemetry is the wireless data transfer that happens between the drone and the ground station. Mavlink is a communication protocol that you can understand it. PID control is a stabilization algorithm that stabilizes any system that we give it or apply it to. EKF, that stands for extended Kalman filters, is a sensor fusion algorithm that fuses readings from multiple sensors and gives an accurate output. Waypoint is just in the GPS navigation point. A failsafe is an emergency safety action that must be implemented in your drone systems. Then we also have SITL, that is software in the loop simulation. And we also have flight controllers, that is the same thing as the main onboard controller, but it is also the electronic brain of the drone. That's it for my presentation. If you have any doubts, you can put them in the chat section and I'll keep clearing them. If you have any more doubts, you can personally message me as well. And if you would like to learn more about technologies like SLAM, PID controls, sensor fusions, then you can also check out the aerospace program that is available on the UGAC website, and it has the aerial robotics course under the technical summer school section. Now, I would like to call on Jeevan to explain to us what IMU physics is. Jeevan, are you there?
Yeah, yeah, and there. And
All right. So I'll just stop sharing.
so, good evening, everyone. I'm Jeevan. Now I'm going to explain about IMU physics. So, what exactly is an IMU? IMU is an inertial measurement unit, which is an electronic sensor that is used to measure linear acceleration, angular velocity, and magnetic field. Let's go to the history. Earlier IMUs were large mechanical gyroscopes, which were primarily used in military navigation. They were bulky, expensive, and high power consuming. But whereas modern IMUs, they use MEMS technology. They are small and consume low power. They are cheap also. So why are we using an IMU? The applications of IMU include knowing position, velocity, orientation, and stability. The data that we get from an IMU is used in drone stabilization, vehicle navigation, motion tracking, and autonomous systems. So, there are mainly three components in an IMU. The first one is accelerometer, which is used to measure acceleration. Second one is gyroscope, which is used to measure angular velocity. The third one is magnetometer, which is used to measure the magnetic field. And there are generally two configurations in an IMU. First one is 6-axis IMU, which has three accelerometers and three gyroscopes. And the second one is 9-axis IMU, which has three magnetometers and extra to the previous configuration. Here is an example of an IMU, and this sensor's name is MPU6050. It is a 6-axis IMU. So let's understand how an accelerometer works. So basically, accelerometer has a movable mass, which is fixed to the frame using springs. But in reality, they are not exactly the springs. As you can see, the moving mass can move along only one direction or one axis. And this axis is called sensitivity axis. That's why we use three accelerometers to measure the acceleration along three axes. Yes. Uh, when the mass moves because of the external force, it changes the distance d between the fixed plates of the capacitor, variable capacitor, and this changes the capacitance according to this formula, C equals to epsilon naught A by D. So here is a video showing how the plates, distance between the plates changes. Uh, the capacity of the variable capacitor is measured using an ADC, analog to digital converter. To increase the sensitivity, accelerometer has more than one variable capacitor to in connected in parallel. You can see them here like this. Here there are four. The ADC returns a numerical value that expresses the voltage of the across the capacitor. And by using the reference value in the reference value of the voltage in no motion state, we can find the voltage difference. And by using the sensitivity value, which maps the change of voltage for each G value, we can find the acceleration. And this sensitivity value is given in the data sheet of the sensor, IMU sensor. Here is an image showing the internal structure of an accelerometer, which is used to measure horizontal and vertical accelerations. So the output of the accelerometer has acceleration due to gravity included in it. So this is the acceleration due to gravity. If you want, we can subtract it from the measured values. And there is a noise, which is mainly due to vibration. So let's understand how a gyroscope works. both gyroscope and accelerometer has a moving mass, but in gyroscope there is a different mechanical design. So gyroscope mainly uses Coriolis force or Coriolis effect to find the angular velocity. It has a resonating moving mass, and whenever there is an external rotation applied, the Coriolis force deflects the mass, which is used to calculate angular velocity. Since we need a constantly resonating moving mass, the gyroscope consumes higher power than the accelerometer. So the output of the gyroscope has the drift included in it, which is like an error term, like since we write delta W like that term. So let's try to calculate pitch and roll angles using accelerometer. Mm, This is our x-axis, and this is our y-axis, and this is our z-axis. So when the plane is rotated about x-axis, it is called roll, and when the plane is rotated about y-axis, it is called pitch, and the plane is rotated about z-axis, it is called yaw. The diagram below shows how pitch is derived. The surface containing the IMU sensor, it is rotated about y-axis. That created an angle of theta, and which makes the which creates two components of acceleration due to gravity along x and z directions. Here you can see the components, and from this diagram we can write tan theta equals to ax by az. From that we can get theta equals to tan inverse of ax by az. Similarly, we can calculate roll by rotating the surface about x-axis. From that, we can get tan phi equals to ay by z, and phi, that is the roll angle, equals to tan inverse of ay by z. So let's try to compute the pitch and roll angles using gyroscope. So since gyroscope provides angular velocity directly in degrees per second, we can simply multiply and get the theta value here like this. Uh, Pitch angle is equals to the theta naught. It is the initial pitch angle before the delta t time, and omega by this is angular velocity about y direction, and this is the time lapse between the two readings. Similarly, we can find the roll angle also. Here is a graph of the values that we computed now. So the accelerometer is more sensitive to vibration than the gyroscope reading, and as you can see, the gyroscope value is slowly drifting over time. So we need to fix this. We use calibration to fix this. Calibration will make sure to give the reduce the drift to the maximum value. So now after calibrating, we can see the graph, it is very smooth. So for better readings, we use complementary filter. You'll study more about complementary filter in sensor fusion part, which is covered by Divyanshu. So now we try, and we are going to try how to compute yaw angle. We cannot determine yaw angle using accelerometer, since it will not produce any component of acceleration due to gravity when we yaw a plane or any object. So, but we can find from using compass and gyroscope directly for the yaw angle. Here are some references. That's all from myself. And if you have any doubts, let me know in the chat box. Handing over to Goel.
Okay. Let me share my screen. So is my screen visible?
Yes.
Hello. Okay. So hello everyone. I am Divyansh Goel from Aerospace Department and Aeromodelling Convener of Current Tenure. So let's talk about sensor fusion algorithms. So what sensor fusion actually is? As the name suggests, sensor fusion is combining the data from multiple sensors to get the accurate state of our drone. We basically want to know what's the state of our drone currently, what is the orientation, in which direction our drone is heading. For this, sensor fusion plays a major role. So why we should use sensor fusion? Because See, we get some reading from single sensor, but it is not enough alone to determine the position of drone. We need to continuously know all these five states. First is the orientation, which includes roll, pitch, yaw. Another, the position of drone, and we should know the velocity of drone, what's the speed, and the altitude where our drone is, and the direction in which it is heading. For this, sensor fusion is necessary. Here's a graph explaining why we should use sensor fusion. So, uh, we can talk about the gyroscope. It is basically used to measure the tilt angle, but the problem with gyroscope is that the drift accumulates over time. It is not reliable for long-term motion. And on the other hand, the accelerometer, which measures the tilt angle only, it is stable for short term, but for long term, it is very noisy. So we're gonna talk about some limitation of sensors, which basically reflects the use of importance of sensor fusion. First is the gyroscope, which measures the angular velocity. The advantages are it has a very fast response and excellent for short-term motion. But the problem is for long-term motion, it will throw a large amount of error. For example, the gyroscope will measure a certain angular velocity, but we need to calculate the tilt angle. So we have to integrate it with time. Let's say you have a zero point 0.1 unit of error at time equals to 1 second, and you have to calculate the tilt angle after 10 seconds. So, talking about the error, it will get multiplied by 10. So, when the error was zero point 0.1, it will now become 10, 1, which is significantly larger than zero point 0.1. So, that's how the concept of drift works in gyroscope. And similarly, for accelerometer, which measures the linear acceleration and ultimately the tilt angle, the problem is it is very noisy due to the movement and vibration that is affected during the motion. Another for magnetometer, which measures the earth magnetic field to know the direction in which our drone is heading, basically yaw. But the problem with magnetometer is that it is sensitive to electromagnetic interference, which is caused by the other sources like ESC, motors, wires and all, which disturb the reading of magnetometer. For a barometer, which measures the altitude of our drone, the main problem is change in pressure. It may be due to weather or a propeller wash effect. Basically, propeller wash effect is when the propellers are rotating, it creates turbulence around it. So if we place our sensor near it, it will experience a change in pressure, which will affect the reading of barometer. Talking about GPS, which measures the position of our drone. The problem is slow update rate and the signal loss. The major problem is the signal loss. So for resolving these problems, we have some sensor fusion algorithms, which we're going to talk about. There are mainly three sensor fusion algorithms. First is the complementary filter, which is the most basic one. And another is Kalman filter, which is more on advanced side and used in autonomous drone, and extended Kalman filter, which is the extended version of the Kalman filter and is used in industries mainly. Okay, so talking about complementary filter, it is the most easiest and commonly taught algorithm. It basically combines data of two sensors, the gyroscope and the accelerometer. So what basically happens is gyroscope is good for short-term motion as we have talked earlier. For long term, it will throw an error. On the other hand, accelerometer is good for long term and for short term, it is very noisy. So if we combine both these data, we can get a stable and less noisy output, which we want. So complementary filter exactly does this kind of thing. There's an equation. This equation, theta equals to alpha theta gyro plus 1 minus alpha theta accelerometer. where theta is the estimated angle. So in a complementary filter, we take some contribution from both the gyroscope and accelerometer, which is shown as a weighting factor. Alpha is called as a weighting factor, and its value is typically 0.95 to 0.98. So what happens is uh, we let the gyroscope to handle high frequency motion, and for low frequency motion we use accelerometer data. That's how we will get a stable and less noisy data. And we can see that both the gyroscope and accelerometer complement each other in this process. And this is why this filter is called complementary filter. So yeah, working of complementary filter is the high frequency noise is removed, which is due to accelerometer, and low frequency drift is corrected, which is due to gyroscope. And as we can see that it acts like a high pass filter for gyroscope and low pass filter on accelerometer. The uses of complementary filter are for the basic drones and Arduino projects and some of the IMU projects also. But for an autonomous flight, we mainly use Kalman filter. So, as we have talked, Kalman filter is more on advanced autonomous flight side. It is more probabilistic and mathematical. It is mainly based on a model called two-stage prediction model. So, it has two stages. First is the prediction stage, in which we use some physics model, kinematics only, to predict the next stage of our drone. And with these reading which we get from sensor, we correct those prediction. So I explain it again. There's two stages. Firstly, we will predict our drone state. Then we'll get some sensor readings. We'll compare those reading with our prediction and know how much our prediction is wrong. There is a term called innovation that we'll calculate, which is basically measurement minus prediction. After calculating innovation, we will get to know how much our prediction is wrong. So after correcting this prediction, we will send this data to flight controller, and ultimately it commands the motor to output accordingly. So yeah, workflow is similar. It continuously update the model, the measurements, and it handles the noisy sensor, predict the future state, and adapts dynamically. Adapts dynamically, it means almost 100 times per second, this whole process of two-stage prediction took place. This will help in minimizing the error and a stable estimate of our drone state. But the problem with Kalman filter is that it only works for linear system. But in case of a drone, it's a non-linear system. Linear systems are those in which the output changes linearly with input. For example, if we double the input, our output will also get doubled. But in drone, there are some equations that involve sine theta, cos theta, and omega square types of term, which are non-linear in nature. So for this, we have to use extended Kalman filter algorithm. So what EKF does is it linearizes the non-linear equations. Uh, for this, it uses some kind of Jacobian matrices that we have studied in our MA 105 courses. And this process is called linearization. So if we talk about the workflow of extended Kalman filter, we have a sensor, and by our prediction model, we predict the next stage. Then after getting the reading from the sensor, we send it to EKF. EKF compare both these reading. Then finally, it corrects the reading using the measurement and prediction model. And ultimately, it sends it to flight controller back and get the accurate state estimate of our drone. And EKF is also used in Pixhawk. Mostly the modern flight controller uses EKF, whether it is Pixhawk, ArduPilot. Um, yeah. Talking about EKF in Pixhawk, the modern Pixhawk which we use is that is PX4 software. uses EKF2 algorithm. This is the further more extended version of EKF. And in ArduPilot, we uses EKF3 algorithm. These continuously estimate the drone's altitude, position, velocity with a frequency of 100 times per second. That's a large frequency and it helps to minimize the error. So that's how sensor fusion works in modern drone. We have our sensor. First we calibrate them, then filter out to reduce noise. Then we apply some sort of sensor fusion algorithm that we have discussed to get a state estimation of our drone, and we send it to our flight controller, and ultimately it commands the motor to align the drone in that direction. Uh, so far we have discussed sensor fusion algorithm. If you have any doubt, you can ask in chat. Also, in our aerial robotics workshop, we will cover Kalman filter and extended Kalman filter in further more detail. So let's move to our next topic, that is flight log analysis. So what is a flight log? You can think it of as a black box of our drone system. In a flight log, it is a recorded file containing all the data, whatever it is. It is the altitude, whether it's a GPS data, the input and motor outputs, battery health, and any kind of error that has occurred, or the sensor data, control behavior, everything is covered in a flight log. It continuously record data throughout your flight. And for flight log analysis part, it is really important because it helps us to understand what is the error that has caused our drone to crash. If your drone has crashed, you have to identify that error, and for this, flight log analysis performs a major role. It helps engineer to understand where instability occurred, why crash happened, how our sensor behaved, is there any kind of error in our sensor or the inputs that we have given. Yeah, it is like a black box or investigation system of a drone. So there are some types of flight log. First is the data flash log, which is the most important one. All the internal information are recorded in data flash log. Internal information in the sense all the IMU data inside the Pixhawk, all your internal data, and for a normal flight, manual flight, the data flash log is most important thing. And another, we have a telemetry logs, which is less important than data flash log. But for an autonomous flight, telemetry logs are also important. Uh, they are basically recorded through the mission planner Q ground control that you are using, basically the inputs. And another, we have Mavling logs, which is Mavling is basically a communication protocol between the companion computer and drone. So in Mavling log, the communication data is stored. So in the flight log analysis, we have to basically find the error. And for this, we have to consider some common flight errors. First is the EKF failsafe, which is the failure of EKF. And that can be due to inconsistent data from the sensor and ultimately the sensor fusion failure. Or there might be a GPS glitch, which is due to signal loss or the slow update rate of GPS. Another, there can be a compass variation due to electromagnetic interference, due to ESC's motor and other sort of electronics. And there can be a vibration. Uh, See, vibration is the biggest enemy of a drone. We have to check whether our propellers are loose or there is a loose connection between our wires because excessive vibration can cause failure. So while doing EKF analysis, while doing flight log analysis, we should do EKF analysis because EKF checks the sensor consistency, the health of sensor, and it runs the prediction and measurement model, and it is helpful for the state estimation of our drone. So we should not take chance on that. we should identify the error on EKF. There are some common error like the compass variation, any sort of GPS glitch or sensor disagreement, ultimately the sensor fusion failure. So we have to check upon that because the poor sensor data can destabilize our autonomous flight, which we don't want. And talking about vibrational analysis, yeah, vibration is the biggest enemy of stable drone flight. It can be due to an unbalanced propeller or a damaged motor, or might be your frame is loose due to some screw are loose, and there is some sort of resonance and oscillation occurring. So you have to look upon the vibration analysis part of the flight log. So also it affects the accelerometer data, which will ultimately affect the orientation of drone. So we don't want that. So we need to first check the vibrational analysis of our drone. Yeah, the workflow of flight log analysis is that firstly, you will have your flight and get some flight log data. You will analyze your sensor and check whether is there any error in sensor, check your EKF or identify the error, and finally you will fix those error and improve your performance of the further flights. And for this, we have some softwares like Map Explorer and UAV Log Viewer for viewing your logs, flight logs, to do the further analysis. So, concluding, the ultimate goal is the better stability and reliable autonomous flight of our drone. And obviously, the operation should be safer. So, flight log analysis help engineer understand the internal behavior of our drone, and by analyzing the sensor data, EKF performance, and vibration, and other GPS qualities also. That brings us to the end of our session. Now, I would like to hand over to Parth for concluding the session. And in case you have any doubt, you can feel free to ask.
Thank you so much, Divyansh. So, just to sort of move this session to an end, we'll take a quick look at our Dronexus summary. That is, I'll just present it. Yeah, is my screen visible? Hello, am I audible?
Yes, yes, Parth, you are.
Okay. So, just to get a brief summary. So, on day one, we had the topics drone sizing, eCalc, and INAV taken by Subramanya and Divyan Singh. So we started with frame sizing, how to determine the size of the drone, how to determine the propeller size, the electronics, that is the ESC, battery, and also thrust rule, that is the total weight times 2 should be less than our total thrust, and also the motor choices for our drone. And in iNav, it is similar to ArduPilot, which is flight software. Apologies, it is similar to QGC. And in this, we saw a flight controller and firmware. Why iNav? Its setup, exploring the setup. We also had the flight modes, that is the stabilize, alt hold, loiter, return to home, cruise, acro, and custom modes. We also had the GPS setup, the black box system. And in today's session, we had Pixhawk, ArduPilot, QGC, IMU Physics, Sensor Fusion, taken by me, Jeevan, and Divyansh Goyal. In it, we had the Pixhawk flight controller, the ArduPilot software, and the QGC software. In IMU physics, we had a basic overview of how the sensors worked and the basic principles behind them. So they generally work on the MEMS technology, that is the micro electromechanical systems. We then have the sensor fusion that is used to take a lot of data from noisy data from different sensors, process them, and spit out a clean signal for our drone to autonomously fly. And this leads to the end, that is the drone access flow. That is, we first plan how we want our mission to be. We then design and size. We build the first iteration. We configure it. We calibrate it. And then we just fly and navigate. So that brings us to our end. So thank you all. And feel free to ask us if you have any doubts. And you can learn learn more about these topics, sensor fusion, IMU physics, iNav, and QGC ArduPilot in our upcoming course, that is the Aerial Robotics course on the UGSC website for Learner Space. And it is available under the Aerial Robotics course in the Technical Summer School section. So with this, I would like to officially end the Dronexus meet. Thank you all for being here. If you have any doubts, you can reach out to us. You can also put them in the chat section and we'll have the slides to you. They are in the chat section. And yeah, that's it. So feel free to reach out to us if you have any more doubts, and we'll be more than happy to help you all. So that's it. If you all have any doubts, you can put them in the chat section now. We'll wait for a few more minutes so that anyone else having a doubt can put them in the chat section. Thank you, Vishwajit, for your affirmative words. So, all right, it looks like no one else has a doubt, so we can officially end the meet. Thank you all for being a part of Dronexus 2026, and I hope we see you all soon when the campus opens again. Thank you all.
And guys, we will be sharing